Hello, everyone. Can you hear me?
Yes.
Okay, welcome back. So last time we talked about a simple example of VQE, variational quantum eigensolver. Basically, it's based on the variational principle. So today we're going through more examples, including other variational ansatz, QAOA, and if we have time, we go over some of the new method, including the quantum classical neural network. And then at the end, I'm also going to talk about the application to molecular energy. So maybe before I begin, I actually want to do a poll to see how comfortable you are running the Jupyter Notebook. This is one that I already did some time ago, but I want to see what how much has changed. Let's take 20 more seconds. The more people answer the poll would help me design the later course material. Okay, I'll end the polling. I'll share results. At the same time, let me copy this. Okay, let me paste the result here. Okay, so yeah, so you've all seen the results. Yeah, I think most of you are comfortable, but a few of you still need more time. So today I'm going to go through more of the notebook. Hopefully by the end of today's lecture, you have been brainwashed enough, and then you would sort of accept that you have to use Jupyter Notebook. Okay, so yeah, this is the summary of the variational quantum eigensolver. Basically, you want to formulate the problem in terms of Hamiltonian, the sum of some Hamiltonian terms. Usually these HI Pauli operators, product of Paulis, and CIs are constants. So what you need to do is for each individual Pauli terms, you need to design a circuit. Mostly the change will be in the measurement. So at the end, you perform the measurement and read out the result. You pass the result onto a classical adder, a classical computer, and then to determine the next optimization parameter to prepare the state. So what changes is the state preparation. And it loops through these until the process converges. So that's the summary of VQE. Any question on this? Okay, if not, few examples that I'm going to talk about include problem in optimization. So this is going beyond physics domain, but we can always formulate these problems in terms of Hamiltonian. So the first problem is the so-called MaxCut. So imagine you have a graph and there are nodes or vertices here with edges connecting them, and you want to cut or separate the vertices into two groups so that you maximize some gain in terms of the weight. So there is a weight between 0 vertex and 1 vertex, 1, 2, etc. Zero, 3, you want to cut into two groups so that the weight along the edges that you cut is maximized. So it can be described by this cost functions. The xi and xj are binary variable, as I indicated here. So you can see that if you consider neighboring one, and if this is 1 and this is 0, that means they belong to different groups. Okay, 0 and 1 indicate two different groups, and you want to maximize the cut across that. So if this is 0, this is 1 and that's 0, you will you would gain a weight here. So you can write this in terms of a quadratic sum of these variables. Yeah, so this defines the problem. So the detail of how you define the problem is not that important, as long as you can find a way to write into some cost function involving these binary variable. Then the next step is to turn the binary into plus minus 1, because in our quantum computer, we can have observable sigma z whose eigenvalues are plus and minus 1. So this would turn this into a Hamiltonian. Let me not call this Hamiltonian yet. We can turn this into this cost function into a operator, a quantum operator. Okay. These 1/4, these are just proper normalization here. And in principle, you could also add a diagonal term. So in the above expression here, there's nothing regarding the diagonal part, but you could put also weight on the diagonal. And then you sort of put a minus sign, because the weight, usually we maximize the cost or maybe the gain here. But this in turn is minimizing the bracket here, which we will call this Hamiltonian. So we want to minimize the Hamiltonian. So from now on, we just need to consider this Hamiltonian and use the VQE and to determine the cost. Okay. Yeah. So basically, what we said last time is that we need to construct a quantum circuit to parameterize a wave function. Right. So an example here is that you may start with all plus state. So this plus is actually plus, plus, plus. And then you go through some quantum circuit, which may entangle entangled qubit, and you could also have a single qubit rotation, etc. Okay, and at the end, so these rotation involving parameter, these can be optimized by using quantum computer to evaluate the cost here. And you can use that value to determine what would be the next parameter you need to put in to optimize, to update your state, and looping this, it will optimize the parameter. So that's the idea. Any question on the setting so far? Okay, if not, let me share the notebook. Let's see, where is my notebook? Okay, so this is a notebook that it's downloaded from the Qiskit tutorial, but I have the file downloaded, and it's in the Blackboard or on my course website. You can follow the link to download the file that I ran. Okay, so there's some description there. So this is called MaxCut and weighted because the edges can have weight which is not necessarily 1. So we went through this, and let me go through the code part. So you can download the code and run it yourself. So of course, in the beginning, you load a lot of packages. The problem is defined, in this particular case, it has a graph. It's generated using the so-called network package. This NX is a network package. So the detail how to use that is not so relevant at the level of discussion. Here you can always look up the documentation. But basically here is to create a graph, and you add nodes, and there are 4 nodes. It's indicated here, label 0, 1, 2, 3, and you want to put edges. So edges, according to the first 2 index, 0, 1 is an edge, and you put weight on that. So this basically creates a weighted graph. Okay, and let's just draw the graph here. So let's just draw the graph. Okay, so this graph with the weight on edges define the problem. Okay, so the weight is, so, okay, the weight is not, okay, it's created here. But you could also generate it by a matrix. So this also, you could also generate by a matrix from I. With 2 labels, this is a matrix, n by n matrix, and you just, here it's just reading, okay, here is reading that edge data and create this weight matrix. Okay. So this is the printout of the weight matrix. I think it's also possible that you generate a weight matrix and somehow you feed into the edge, yeah, according to whether the element is what. So this could be using the edge between vertex, the second vertex and the first vertex. This could be the second vertex and the third vertex, and they're symmetric. So this W is the weight matrix, and so the following of the code basically said that we can run through this by brute force search. So there are 2 to the n. So I just run through all the possibility. So that's the idea in this block of code. So the detailed implementations that are important, it just goes through all the cases, right? Just go through all the 16 cases and find the cost. Okay, so you can see that there are 2 that are maximal 4, right? And the solution is plotted that using the color to representing the cut is this one example. The math solution 1010. It's just one of them. So you could also take the other one. Okay. Okay. So that's the example here. So next, we're going to see how we are going to use quantum algorithm. First, we have to map this into what we call Ising problem, basically the sigma z and sigma z times sigma z. And this is already packaged well, so you just need to input the weight matrix and just use the so-called MaxCut get operator. This is already built in now in the Qiskit. You get a qubit operator, and you might also have offset. The offset are constant term that ties the identity. So this is the offset, okay? Okay, and you can print out the individual Hamiltonian term. This shows that there are 1, 2, 3, 4, 5, because there are 5 edges, and these are the weights. So remember, there's a factor of 2 when we define the Hamiltonian relative to the cost. Okay, so and you can print out the operator in terms of the dictionary. So this is okay. This part is not that important. Just is a way that you could also write down explicitly the Pauli terms, IIZZ, coefficient, etc. In case you want to write down the Hamiltonian by hand and then inputting it as an operator, that's also possible. Okay. So to create the Hamiltonian, so these are qubit operator. This actually is the Hamiltonian, okay? So it's already created here. But you could also, as I said, you could write a dictionary and list all the terms by hand. And then you can call a function that's a weighted Pauli operator from dictionary. Okay, so you create also the same qubit operator. So there are 2 different ways. And then you want to map this Ising Hamiltonian to the so-called quadratic program. Unfortunately, in the code that come in here from the newer version, in the 0.19 version, that this cannot work. So the way they do that in the newer version is you say from Ising, and then you create a so-called quadratic program. But we need to have some workaround to do that in this version. It's not that important, so I will skip this part because that's the difference of a newer version of Qiskit and older version. Because from that quadratic problem, you can use exact solution, exact diagonalization to find a solution and double check. So you get a quantum Hamiltonian turn into a quadratic program, and you call these functions to solve and find the exact solution. So we've seen the solution like this before by brute force, but here is simply using the built-in function. Okay. This part here of the code, check that the right cost. So basically is getting the solution This is also a very similar way of that. The above is using the quadratic program. We won't discuss in detail, but here we directly take the qubit operator, qubit Hamiltonian, we diagonalize that. We diagonalize that and find the most likely state, and to output the eigenvalues, and we can output the cost objective and solutions. Yeah, and shown here. In terms of the energy, this is minus 1.5. The MaxCut objective is minus 4. I guess they put a minus sign. So then you are finding the lowest one. And this is the solution. So notice that this is 0, 1, 0, 1, because that's the other solution, 1, 0, 1, 0. But they are equivalent. Okay. So I'm going through very detail of the code. But if you can guess the rough idea of the logic, how the program is implemented, that would already be good enough. So next we will see how we'll do this on a quantum simulator. So we will not run actual quantum device, but we'll use a simulator. So this is just saying that I'm going to use a simulator, and I call this a quantum instance. As you can see, it's already built in Qiskit. You can use some variational form that we discussed last time. And this is defining a classical optimizer. This here use a different one, okay. In the new code, you would write the optimizer and limit the maximum iteration. In the old code, it's called max trial. So there's some difference, slight differences in the older and newer version. So here I create a variational form, Ry. Basically, it's a Y rotation, and then an entangling gate. If beyond 1 qubit, you will put entangling gate. I think this is using Control Z. The entanglement is linear, meaning that you only have entanglement. Control Z can apply between the nearest neighbor. And we'll use the built-in package called VQE. We only need to input the Hamiltonian, the variational form, the classical optimizer, and what device we run, called this quantum instance. And that's setting up the program. And then to run that, you basically say the program VQE.run on this quantum instance. Okay, and we denote this as a result. So just like the previous exact diagonalization part, we can just sample what's the most likely solutions, print out the energy, etc. So as you can see, using the VQE, we obtain a minus 1.49, very close to 1.5. And the MaxCut objective is closer, very close to -4, etc. And then this is the solution. In fact, this is one of the solutions. Yeah, so that's, you can actually, instead of saying I'm going to run on a simulator, if you have an account, you can say I want on a real device. Okay. Any question on this part of MaxCut? Okay, so if not, let me go back to the slides. Okay. So basically, this summarizes what is needed, right? So once you define a Hamiltonian, you just need to use a variational answer, and you have the freedom to choose what kind of answer you use, and you run the quantum computer on that and measure the expectation value, and then you use the classical optimizer to show what next set of parameter I need to choose. So that's the idea. Okay, we already saw this.
I have a question.
Yes.
Because we use the quantum state, we only can use the matrix of 2 to the nth power, right? If the problem is not that number, we cannot use this quantum method to solve
yeah,
this.
so the way we turn this is we turn, so you have n nodes, right? You basically turn it into n qubit. You basically turn that into n qubit. So it's always exact, right? There's always exact mapping between the 0-1 binary number to a qubit.
No, I mean the actual matrix, you have to be 2 to the nth power.
Yeah, so what I'm saying is that once you get to the Hamiltonian part, it's always 2 to the n by 2 to the n. This is by design, right? This is a binary variable, and you map to a quantum variable.
I see. But for arbitrary matrix, the eigenvalue problem, you only can solve the 2 to the nth power problem, right?
You solve 2 to the n by 2 to the n matrix, but if the n is too big, you cannot solve it using classical computer, right? So that's the power of using quantum computer. If n, let's say, if n is 30, it may be beyond what you can do classically. So you would use quantum computer, you create a state, and you perform measurement. Okay.
Yes.
So the next one is the traveling salesman problem. So quickly go over that, and maybe this is also related to the question that you just asked. So suppose you're the 3 city and you want to find a path to go from here and back. Well, in the 3 city problem, it doesn't matter how you go, but if you're more than 3 and the graph is more complicated, how do you go from the beginning and then go back and return, and with a minimum cost of time? Okay, so this is optimization problem, has nothing to do with physics, but we can see how it's set up so that it turned into a Hamiltonian. So there are some requirements. So I describe the problem here. This is also in the notebook. So there are n variable that's going to be used. So n square variable. N is number of nodes that has to visit. So the way to set up the problem is use n square binary variable, and because that you need to visit all the cities, so the number, so P is the location of the city, so city 0, 1, 2, etc. P, you need to visit all the city. So the way that's set up is you can see this 2-dimensional array. This is go to step. Maybe you can also call city. This is the, okay, this is the time step, and this is the node. And so if you have a valid path, then you would put a time step 1 that we are here. The time step next, we are at this node 1. Next time step, we are at node 2, and we put a 1. So this is sort of the simplistic way to set up the problem. So you can see that in this 2-dimensional array, you sum over the nodes. It has to add up to 1, and you sum up with the time step, but also 1. So there's a constraint there. So in order to solve the n vertex problem, we use n square variable. So I think it may not be the most economic way, but this is the way it was set up in the notebook. Okay, but then what do we want to optimize? We want to minimize the time, right? We want, in some sense, we want to minimize the distance, the total of the distance. So the total distance is basically the weight in the edges, right? It's edges. And this is very similar to what we have previously. This is the location. Remember, I have this xip. There's another x. If the next time step you go to that node, that means this edge weight is included, right? So you sum over all these possibilities. That's define the cost function, and we want to minimize this. Okay, so when we turn into a Hamiltonian, then we don't need to put a minus sign. Okay. So these two are the constraints that we have in the previous page. Okay. The way to impose a constraint is put 1 minus that and take the square, because and put a constant. If this a is big enough, when you minimize this, this should be close to 0 in the bracket. Okay. Okay. They also have a comment that you don't want it to jump from one node to another node that are not connected. So they could put a constraint, but they say in this problem would be a certain fully connected graph and not include this term. Okay, basically ignore that. But anyway, so the final cost function is this. And the next thing is to turn this into, okay, I didn't put in text, but we turn this into, so 0, 1 into z variable. So remember, you could, in the previous setup, we use x equal to 1 minus z over 2. Here we can also do the same things. X equal to 1 over z over minus z over 2. Okay. And then turn z into operator. Okay, so we would have a Hamiltonian. Okay. Then we simply minimize the Hamiltonian. Minimize this. Okay, with the state has some variational variable. And from the wave function, we can obtain the solution. Okay. So I'm going to the notebook. So you see, it's very similar setup, except that the Hamiltonian is different. So there's some description in the notebook. Yeah, as I showed in my slide, we create a 3-node problem. So it's plotted here using the same network package to draw this. And first, they use the brute force search and try to find what is the solution. But in this problem is really trivial. You go from 0 to 1 and 2, or 0 to 1 and back. They're all valid solutions. Okay. So then you map to the Ising problem. So as I said, you turn individual term into product of z operator and identity operators. Let's ignore the quadratic program because that allows you a different way of setting up the problem. Then, okay, here is the using exact diagonalization, and then find the best eigenvalues and eigenstates, and you can print out what's feasible and the solutions. Yeah, so what's found here is the solution is 0, 1, 2. Okay, 0, 1, 2. Objective is adding up the weight here. This is a trivial problem example. You could modify the graph yourself if you want. Here is where you can modify the graph. Here, so you can set different number of nodes, and then you can set it away yourself, and you can draw this. Maybe have more 5 vertices, etc. And you can modify the code. So the idea is that if you look at this code, you are able to modify the number of nodes, parameters, and run the program. I think that's already is a big step forward. Okay. Now running on quantum computer is the same. So you define your classical optimizer, variational ansatz. So you could change the variational ansatz. There's also the RY, RZ, or swap RZ, etc. Then you set up the VQE program using the converted Hamiltonian operator, variational form, and the classical optimizer and the quantum instance. So you simply run this, you would obtain the result, and then you can check the solutions. Right? That's checking the solution and drawing the diagram. Yeah. Again, this is a particular example is very trivial, and we actually using simulator, so we get very close to ideal solutions. And it may happen that if you run on actual computer, it does not give so well results. Okay. So any question on these two problem, MaxCut and traveling salesman problem? So I hope by the time you feel comfortable going through the code, even though you do not know how to write exactly, if you can read through that and understand, that is already very good.
I have a question.
Yes.
So why do we have to go from the X basis to the Z basis? Because X is just...
X is 0, 1, but our measurement, we get +1 and -1.
Okay.
Yeah. It's not going from the X basis to Z basis. X was just a notation.
I see. Okay.
Yeah. So we didn't change the basis. We just fit the operator so that plus and -1 eigenvalue corresponding to 0 and 1 variable.
Yeah. Okay. Thanks.
So sure. Let me get back to the slides. Okay. So these are applications that outside physics, chemistry, but basically optimization problem can be used to run on quantum computer. So that means that potentially quantum computer will be very useful, right? You can see that these non-physics problem can be solved on quantum computer. Okay, so notice that in the code I try to make it work on the 0.19 versions. So I hope that if you use the notebook, you can run almost all the lines. But if you download the latest notebook, you have to also upgrade to the latest Qiskit version. Okay. So next is something called quantum approximate optimization algorithm. This, in some sense, is another variational wave function. This problem was designed also to solve MaxCut and other problem called max 3 set. So we already seen the MaxCut, right? So you want to cut so that the weights sum over all the weights that on these edges cut by this divider add up to maximum. Another problem, optimization problem, usually encountered in computer science is called max 3 set. It's basically 3 set is, this is satisfiability problem. You have variable, Boolean variable, or 0, 1 variable, x1, x2, etc. 3 set meaning that in each, the so-called clause, you have 3 variables. And these variables are in this logical function, and this combined more of the 3 variable clauses and give you a problem. And you want to, actually 3 set is NP-hard problem. To find a solution that check whether this is satisfied by, or the variable is actually really hard. Another also hard problem is to solve if it cannot be satisfied, but what is the sort of maximize the cost. So this is also a hard problem. Okay, but let me talk about the QAOA itself. It's a variation of ansatz. So the ansatz may look complicated here, but it has a pattern. So it begins with a plus state. So we usually start our computer at 0. So all these become plus states. Okay, so we start with plus state, and then we apply some gate, which is related to the problem, the cost itself, because these are classical problem. I can write in this way. So in terms of this operator, it can be an entangling gate. So this is similar to the CZ gate, Control Z gate, but this is a big entangling gate. Then the next block that I do a rotation, you see that this is rotation in the X basis. I think this should be beta 1. So all these are rotate with the same angle. That's one layer. You can repeat this structure, another layer. You apply these another rotation, but these are so in the Z basis with a different variable, and a single qubit rotation with a different angle beta 2. So you start with gamma 1 variable, beta 1. This is the layer 1. Layer 2, you have gamma 2, beta 2. And in general, you can have P layer. But of course, for the present quantum computer, you don't want to have too many layers. But the upshot is that once you have these ansatz, you want to maximize the cost here, and you basically are maximizing this. So we are going to use quantum computer to evaluate. Right. And choosing, or let's say optimize gamma, beta by classical computer. Okay. Yeah, so this is the circuit again. Again, this is should be beta 1. Yeah. So a simple way to do that is to do a grid search. So for example, this is the cost function, cost in terms of this. So if you are able to calculate this cost function in terms of these variables, then you can plot this. So in terms of quantum computer, we would evaluate this on a grid. Right? We can evaluate this on a grid by choosing appropriate gamma and beta on this grid, and then we can identify approximate the best value. So, and maybe once you find one, let's say somewhere here, you can do a iterative search to find the maximum one. Yeah. So, or you could do totally optimizing by starting something random and using classical optimizer to search the best beta and gamma. Use any of your favorite optimizer using gradient descent or other method that we have seen a few before. Okay, so in my opinion, this is in the framework of EQE, this is a special case of EQE. Although the way it was invented was from adiabatic quantum computation, so slightly different context. So the Qiskit implementation would look at also the MaxCut, but in this particular notebook, it would use the fine node like this, and the weight on edges are all 1, but you want to maximize the cost. So here you can probably guess, so maybe the cost would be cutting this and that, and maybe the best cost is also 4. So let me quickly go through the notebook. It's very similar to what we've seen before, but using a slightly different functions. So can you all see the notebook, this QAOA part?
Yes.
Okay. Since we are dealing with the MaxCut, so of course we use the network package. We build this node and weight. Okay, the weight are all 1. And this is the graph with weight 1 on these edges. So first we can evaluate the functions. This was the one. Okay, so here we use only one layer. So there's only alpha, beta, and gamma 2 parameter. So that can be directly calculated. The cost can be directly calculated. So we can then make the plot of the cost function. So you see the solutions are here. These are local maximum point, right? So that's the, for example, and you can do the grid search. So that's what's done here using classical means. And it's found that maximum expectation value is 3.4. That's the gamma and beta function, but these using the grid, so not necessarily the best solution. Okay. Now to do the QAOA, we create a quantum circuit. This applied Hadamard gate, we get a plus state in the beginning, and you apply the Ising gate, right? So there's a control phase. So this is control phase gate between K and L with the 2 gamma. Okay, so basically this is implementing the first plot of gamma rotation, and then you do the X rotation. Yeah, so this applies to all the qubit. The factor of 2 may be just because the Pauli matrix is rotation, etc. But if you might as well use gamma or 2 beta, just changing your range of parameter from 0 to pi or 0 to 2 pi accordingly. Okay. So then at the end you perform measurement, and you can draw the circuit here. I don't know whether I can go. Okay. Yeah. So this circuit here is showing the purple is the control, and the U1 is just to implement that gamma rotation. So all these are just used to implement that. I think I'm not, okay. I can scroll this to the right. So that's the end of the first gamma rotation. Then you perform X rotation. This is one layer, and so immediately at the end of one layer, you perform measurement. Okay. Okay. Yeah. So the cost function, you have that expression. So once you have that, you can plug in your measured outcome. So because you measure all the qubits, it's either 0, 1, and then you can plug that into this to get, so your X will be a string of 0 and 1 obtained from measurement. Then you can plug in this so you can evaluate that. Okay, so this is very simple because you can see that a lot of things are built in. You have the quantum. Okay, here is not using any of the built-in, but you just need to design this circuit. It's very simple. One layer of the rotation in a Z basis and one layer of X basis. Okay. So here also using simulator, but it's not using the state simulator, state vector simulator. It's using the quantum assembly. So you need to let the simulator know how many measurement you want to run. Okay, so you basically said you execute this circuit, what kind of machine I want to run and how many shots. You obtain the result, and then you can plot the result. These are the 0, 0, 0, 0, 1, etc. and the probability. So to get the optimal solution, we should use the one that has the best of probability, and then check the solution or check the cost. So for example, to check the cost through here. So this is, you get the count from the measurement, and you evaluate that. So this block is just to search what is the best. Okay, just compare. If the cost is small, then I replace by the bigger one, and then at the end I output the cost. Okay. Here also organize the distribution of the cost. You can see 0, 2, and 4. 4 here has a peak and has more weight there. Okay, and then it print out, draw the cut according to the color. Okay, so this is very simple because it's also an example of VQE. So any question on this?
So what about the local minimum?
Local minimum. So the idea, okay, that's a good question. I did not talk too much about why they want to. So you have local minimum, right? Yeah. So you might also have solutions that are minimum. You might also have solution that could be minimum, but these probably is the one here, 0, but has a very small probability. So the idea of using, actually this is the maximum minimum. There's the local minimum are also yeah, except, okay, but these other points are set up point. These minimum are the maximum minimum. So the idea of using the X rotation, right, is because that X rotation is a different basis than the Z rotation and the Z basis. So that would allow you to tunnel in some sense. If you get trapped here, you might be able to tunnel to other places. Yeah. Okay. So I did not talk about the physical reasoning and how it related to the adiabatic quantum computing, because we have not introduced the adiabatic quantum computing. But we can come back later when we discuss the adiabatic quantum computation. So I want to see if you have any other questions. Okay. So I want to also mention other topic, but these VQE and QAOA, they are the current research topic. Of course, the subject that people discuss is beyond these naive implementation QA. How do you improve this and how do you optimize? There are also other variations on this method, but these are the sort of the basic foundation that people are based on recent research topic. So another different but also really interesting direction is to sort of combine the classical neural network machine learning and using quantum computer. Yeah, so we know the classical machine learning has become an important tool. Probably the newest, the latest focus in science and technology, there are two important ones. One is the AI, the other is quantum technology. So why don't you combine the best of the two into one? So that's why people are looking at quantum machine learning. So this is really a recent and really active research topic. So I took this from this picture from the Qiskit textbook. So the idea is you want to combine the two. So it's a hybrid approach. So there are some classical way of building up the neural network. There's some classical nodes. So we don't really need to worry about the detail. Maybe some of you have a lot of knowledge already on machine learning. There's already some package you could use, a PyTorch. Even Google has its own package that can be used. And we would like to sort of output some of the output there of the classical neural network to quantum computer, and then using quantum computer to evaluate some of the costs using VQE, QAOA, and these parameters are sort of trainable parameters. And then we output, so we can optimize and then feedback to the loop, and very similar to the VQE. So in some sense, you can really see that this is a more general setup of VQE, but just using classical computer, classical neural network to do that. So PyTorch is another Python package that you can use. Okay, so I don't know whether I should go through this. This is not really important, but I just quickly go through the classical neural network. But maybe I can pause to see how many of you have heard classical neural network. I know a couple of you are from computer science. Maybe applied math people also have learned that. And I have to say that I'm not an expert in this field, but I collect some of the material just for my own understanding. Yeah, a few of you raise hands. So basically, yeah, the classical neural network is sort of a way to understand how our brain work. So, and there's something called perceptron. Basically, you have some binary input, and these are all collected into a neuron, and then the neuron decided whether it want to fire, it want to send a signal to the next neuron. And to model whether it want to fire or not, you will have some weight. So depending where you get the input, you weight these signals, and then to see if it's let's say below some threshold, then I do nothing. If it's greater than some threshold, I send out the signal to the next neuron. Yeah, this is called perceptron. How to determine whether you want to fire or not? You could also have other function. This is called sigmoid function. If you're a physicist, you will see that this looks like this actually is Fermi-Dirac distribution. And so the output of that is not binary. So you can generate the binary whether I send out a signal or not. Is I can do like a continuous variable output. Yeah, and you combine all these into many layer of network, it become more complicated. And at the end, the goal is to decide something, decide a function, to compute a function, or decide whether I want to do this or not, whether I want to do my homework now or want to postpone. This is what the neural output will tell you. Okay. Yeah, so I don't want to go through the gradient descent. So what is these gradient descent and other method about is you want to optimize the weight. These each line representing a weight, and maybe you also have threshold, local threshold on each neuron. But the idea is that you want to optimize these rates, maybe to learn a function, and then from that you would get an optimized neural network that could help you to determine like a future input. Okay, so the gradient descent, or a subset called stochastic gradient descent, is a way to optimize these variables. So, but it's not that important in this context here for our understanding of using quantum computing. Of course, you want to optimize, and there'll be cost function. So, what is said here is because to do the training of the neural network, you need to somehow input the known data. If I know, somehow you train this in the sense that you learn some problem, you know the solutions. By training the problem and solutions, then you can optimize that, and that cost is really that. So for example, I think yi is the solution. In this case, maybe we want to do classification 0, 1, 2, 3, 4, the 10 numbers that you want to classify. These y are labels of that in the vectors. So basically, this cost function allow you, if you optimize, then the cost function should be as small as possible. Okay, so but these are really some detail how you design the neuron, how you pick the cost function is also not necessarily fixed. Okay. For the purpose, what we want to talk about today is we want to have an image. So for example, I may write a 0, or I may write a 1. I want to distinguish 0 from 1. And the network that's being used is also convolutional neural network. Basically, it's just cross-graining this. So in some sense, you want to process the image and use a different way to sort of doing some feature map that create a few different way of interpreting the data, and then you sort of do some cross-graining, further cross-graining, and then you output to a fully connected neural network. Yeah, I think I'm explaining too much, but just try to fill in the gap as much as possible. Okay, so these are really detail how you do the cross-graining from here to a smaller one, but at the cost of more layer. Yeah, these are called feature map. But then once you have that, you would shrink to a smaller size, and from this you would use the network that we have here previously. Okay. Okay, so but that's really a maybe 5 minutes overview of neural network. It's, to me, would also be too much, but I hope you get a rough idea of what this is about. So basically, you want to combine the input to the quantum computer can be directly classical data, but can also be a reduced size from a previous classical neural network. And you would perform the measurement. This measurement can, for example, be fed back to this and then classical optimizer, but that could also be combined to a classical neural network. So in some sense, you can, if your viewpoint is from a quantum computer, you can view these classical neural network is a way to help you optimize the parameter. Okay, I think if you take from this viewpoint, then you probably don't need to know the detail of that, of these neural network. Okay. Yeah, so any questions so far, or anything from computer science people who want to comment or correct my understanding? Okay. Okay, if not, let's see how much time we have. So we have about 15 minutes, so we can go through the notebook. So I'm going to share the notebook. Of the hybrid classical neural network. Somebody asked what's RH1. Which page did you see that? Let me go back to the RH1. Oh, RH1. This is basically rotation. Rotation depending on the output of the classical neural network, right? You output a H1, and according to the output, I do a rotation. So this is basically the angle of rotation, but it does not specify which angle, which axis I want to rotate. So this is a really a schematic of the quantum circuit, right? Okay, let me return to the notebook. Okay, so yeah, so in this notebook, we will use this PyTorch. So you have to install that. And we will use this, their neural network packages. And here they define an interface. Yeah, define interface to the quantum circuit. So here would be, is going to be a circuit and number of qubits and which machine, what kind of machine which back end or I want to run and how many shots. So these all created that, and how I run the quantum circuit. So basically you've seen this, it's execute, read out the results and get the counts, right? And you can calculate probability, expectation value, right? So this is creating an interface, okay? And the simulator is the usual simulator, the quantum assembly simulator. So an example of circuits is here. So 1 qubit, right? So this is using the interface here. Quantum, this class circuit. 1 qubit, in this example, 1 qubit. The back end is the simulator, 128 shots. So you see the example that I ran below actually use more than that, but it takes a lot of time. This take a lot of time. If the number of shots, meaning the number of measurement you want to repeat, if it's a large number, then this running this would take a lot of time. Okay, this. Okay, so that's the circuit. So you can draw this circuit. There's also the hybrid function. This is the part of quantum classical. In the classical one, there is some, okay, you need to find, the gradient. In order to do the gradient, you would sort of evaluate your rotation angle a little bit plus and a little bit smaller. So that's what's here, shift right, shift left. And then you get a gradient by calculating the difference. Yeah, so the gradient is calculated here. Okay. And here, and so they all obtained from the measurement quantum computer. Okay. That's the quantum part, and the hybrid part is you use the quantum and hybrid function apply that define the forward. Forward is probably forwarding the neural network result. Okay. So, but in this set of notebook, I guess you don't need to worry about these. These are already built-in functions, functionalities, etc. Let's just see how it works. So first, they're going to do the training and recognizing 0 and 1, as you can see these images here. So there's something called MNIST that you download. You can download the images. So it's downloaded here. Okay, and then we only select the 0 and 1, 0 and 1. There are 0, 1 to 9, but we only doing the 0 and 1 discriminator here. So as I said, you need to train the data. So you load a large number of images that you know are 0 and you know they are 1 and separately. And you use this set of data for the quantum computer to train in order to optimize those network parameters so that you have high percentage of getting a 0 and 1. So you're really using the known data, right? So in some sense, this is cramming a lot of information to the hybrid quantum classical neural network. So these are some examples, right? So these are some example of 0 and 1. So once you have trained that, right, so this is really trained, it hides a lot of detail, okay, into the already package. So the functionalities and also, yeah, how the classical neural network is doing. Okay, so once you have optimized your neural network, then you can use additional sample to test. So this is basically to load additional sample, and to load those are 0 and 1. You know the answer, but you don't want so that the answer known by the network or the hybrid quantum computer, classical computer, and you perform that and ask these neural network to predict whether it's 0 and 1, and you keep a score of the correct 0 and 1 that give you a accuracy. Okay. So they also define a class network here. It's really using the convolutional network that I briefly sketched and define what's the thing that's forwarded. Yeah, that detail is not that important. So I don't think I understand every line of the code myself. But the way to do that is just call this function net and do the optimization. So far here, we only define, I think we only define these, but the actual runs taken place here. So you have a loss function and you train here. So this is the major part of the actions. So you load a batch of data, and optimizer do the gradient, zero gradient. You output and loss, and do the backward. So there is something that I gloss over. I think there's a, when you do the gradient, you need to somehow propagate the gradient all the way from the beginning to the end. That's some detail that I don't want to discuss. If you're a CS person, you know the neural network, you know this. But if you're not, then it's okay. I probably will not have time to explain to the degree that you understand. In a sense, it's doing the gradient using chain rule. How do you propagate this to the next layer or the previous layer, so that you save time in not repeating things that you already calculated. Okay, but I think this is more detailed than I wanted. So you basically load the data, and you do the training, and you keep track of how much you train the data and loss function, etc. So this is plotting the loss function. It generally should decrease, and when it converges, it should stay flat. And then you can, I think this is evaluating the performance. So you can see that the performance on the test data has 100% accuracy. So let me see, this. Okay, so this, you take a particular sample to, let me see. Yeah, this is test. And there's also the final one. It's just to, okay, this is just to output some of the tests that's done in this process. Yeah. So for these examples that use as test, yeah, you predict very well. So you might not get 100% accuracy if you run this. The reason that I may get this accuracy so good is because in the number of shots, somewhere, I forgot where, I think I use, so yeah, here's number of shots. In the actual run, I think I put 2048, but the original notebook only used 100. So I changed number back to 128, so that when you run, it will not take too long. But you can experiment by changing these numbers. Okay. Any questions? Yeah, so I know there's a lot of material, but these are sort of advanced topic. If you don't get the machine learning part, which I think is fine, if you get the idea of you are using the classical computer and use the classical machine learning to help with the quantum computer. Yeah, so okay, these are the examples we went through. Yeah, so I don't think I'll have time today to talk about another advanced topic, but if you're a person from chemistry, you will find this very interesting applications. Maybe we can talk about this, spend some time explaining the idea and then going through the notebook. Yeah, so I would say that the topic I cover in this week is advanced topic, because these are topics that a lot of people are currently doing research on. So don't get frustrated if you cannot understand these material 100% like you have in the previous lectures. So maybe I stop here and see if you have any questions. Okay, no question. So I encourage that you can take a look of what maybe recent research paper on these area. You just search using BQE, QAOA, hybrid quantum classical neural network. You will get a lot of papers that are really in the research. There's a question from the chat. How do you simulate molecular energy since Hamiltonian is infinite dimensional? Yeah, so we will discuss that. So you would choose a finite set of orbital. So your Hilbert space is not infinite. Okay, of course, if you want to solve the problem exactly, you would have infinite dimension, but you know what orbital are most important. So for example, I've shown here, lithium hydride is lithium atom and hydrogen atom. You know which orbital are the most important. So you will not, so for example, you will not take 100 s orbital to be in a calculation. So you truncate your basis. We'll talk about that in more detail next Monday. Any other questions? Okay, if not, we can stop here and feel free to leave. I'll see you guys on Monday. And at the same time, I'll stop recording.